Hello everyone, welcome to another interesting lecture on digital signal processing on FIR filters. So in today's class, we are going to talk about how we can design your FIR filters using window technique. In our previous lecture, we have seen how to design your FIR filters using Fourier series method. So your window technique takes the Fourier design and it just adds a window function to it. So basically what I'm going to do is I'm going to take the Fourier FIR filter design with my Fourier series and then I'm going to multiply it with a window function. So your window functions can be either a rectangular window or a triangular window or a sinusoidal window. So the shape, depending on the shape of your windows, you have different window functions. So what happens is, why we need this window technique, or what is the advantage of this window technique over your Fourier series method? So the main advantage of using a window technique is you get the band limited signal. So what happens is your filter is now band limited to the duration of your window, because normally your FIR filters tend to have a long side lobe and it takes more time for that side lobe to disappear to zero. So if you take the FIR filter as it is, so your side lobes are gonna increase, it's gonna keep a long tail. And now if I am using a window, just as I'm showing here, this dotted line represents my window. And if I'm multiplying my FIR filter with this window, so I am going to contain that FIR filter only inside that window. So whatever is outside that window, that's going to vanish to zero, because I'm multiplying with a window which is only existing in that range shown by your dotted line. So this is a rectangular window. So what we are going to do is the design of FIR filter is nothing but you take your FIR filter and you multiply. You just plain multiplication with a window function W of n, and that's going to give you a band limited FIR filter. The bandwidth is decided by the window width. So if your window is from say -10 to +10, your FIR filter is going to be existing only from that duration, -10 to +10, and it's going to be 0 for the rest of the or outside this range. Outside this -10 to +10, it's going to be 0. So this is your FIR design using window. Now we have different types of windows. So what are the criteria for choosing your window? So you can either have a window which is designed to be just like we saw now. You can have a rectangular window, you can have a triangular window, you can have a cosine window, and you all know that signals with sharp corners tend to produce more ripples. So what happens is when you are using a rectangular signal, or when you are using a rectangular window or your triangular window, they tend to have sharp corners and boundaries. So when they are used for multiplying with your FIR filter, they tend to add ripples. They tend to produce more distortions in your final FIR. So in order to minimize the effect of distortions because of this window multiplication, what we do is we take a cosine or a sinusoidal windows. So the sinusoidal windows, as you know, it's gonna give better response function. So when it multiplies with your FIR filter, it's going to produce less distortions or ripples. So it is very much desired for use in your FIR window designs. So there are three functions. There are three types of sinusoidal, or we call it a raised cosine. So it is a cosine. It is a cos wave which is raised to above the zero axis. So that is your raised cosine window. So we are going to have, we have three functions, namely Hanning, Hamming, and Blackman windows. So these three functions, what they do is they take a 0.5, right? They take this window and they have the shape of a sinusoid. So the Hanning formula is 0.5 plus 0.5 cos 2 pi n divided by n minus 1. So that is your Hamming window formula, and as you can see, the shape is a sinusoidal shape which is desired for lesser ripples and distortions. Now your rectangular window is having an amplitude of 1. So what I can tell is when you multiply anything with 1, you're going to get the same. So which means your FIR filter is going to stay the same. But what your rectangular window can do is the band limitation. So the range will be only from minus n minus 1 by 2 to plus n minus 1 by 2. So your FIR filter will not go beyond that range. So that is the use of using a rectangular window, even though the amplitude is 1, though it is not recommended because of the sharp transitions, you get more distortions. So that is what I'm writing here. So we will stick to this Hanning, Hamming, and Blackman windows. So we are going to solve numericals in today's class, and even the next class we're going to see numericals on these window designs with the Hamming, Hanning, and Blackman. We are going to see how to code them, how to program them in your Scilab. So all those things we'll be saying. So I'll just quickly write the cost functions for the other two windows, which are my Hamming window and my Blackman window. So for my Hamming window, it is 0.54 plus 0.46 cos 2 pi n by n minus 1. Good. So that is your Hamming window. And then for your Blackman window also you have a similar cost function. So now what I would like to tell you is the sum of the coefficients. So in your Hanning window, the coefficients were 0.5 and 0.5. So their sum was equal to 1. So for your Hamming window, the coefficients are 0.54 and 0.46, and that also sums to 1. Good. And I'm writing here the raised cosine because this is normally called as a raised cosine window, because if you see you are not having any negative values, because when a raised cosine is an all positive cos, and that happens when you shift the cos to you shift it by half of the cos you shift above the x-axis, you get this raised cosine shape. So this is the shape we have for all three, Hanning, Hamming, and Blackman. But the perimeter, the circumference, the slope, and all those things are different because of the cost function variance. So now they have the Blackman window is given by 0.42 plus 0.05 cos 2 pi n by n minus 1 plus 0.08 cos 4 pi n divided by n minus 1. So the sum of the coefficients in Blackman window is at again 1, because it's 0.42 plus 0.5 plus 0.08, and that is equal to 1. And this is your FIR design equation. So HW of n is equal to H of n into W of n. And so that is what you are doing. So your H of n is your FIR filter designed with any method. It doesn't matter, but you just multiply it with the window function W of n, and that is your FIR window design. Good. So now we are going to see how to design a high pass filter. So in our previous class we have solved a question on your low pass filter. So today here we are going to see how to design a high pass filter. It is given that the high pass filter is ranged from pi by 4 to pi. Good. So it is given that. So let me draw the frequency response curve for h of omega, how it looks like. So from minus pi to pi, so I'm going to get in this manner. So this is minus pi by 4 to minus pi by 4, pi by 4 to pi, and this is 1 and 1. Good. And now it is only existing. So the value is 1 from pi by 4 to pi. Yeah. So your h of n is equal to 1 by 2 pi integral minus, so the formula for your h of n, I'm writing it here, that is 1 by 2 pi integral minus pi to pi h of e to the power of j omega, e to the power of j omega, and d omega. So your h of n is equal to 1 by 2 pi. So from minus pi to minus pi by 4 it's 1, and from minus pi by 4 to plus pi by 4 it is 0, and then from pi by 4 to pi it's again 1. So just applying the limits, and I make sure that I have the integral limits from minus pi by 4 to minus pi by 4, and I'm going to solve it using the integral formula. Just e to the power of integral of e to the power of j omega n is e to the power of j omega n divided by jn. So after solving this using the integration formula, I'm going to get something like, I can just tell right now it is going to be 1 by pi n sine pi of n minus sine pi by 4n. So that is what I'm going to get when I apply the limits and I do the integral. So let me just show it to you. So I'm doing all the steps because for someone who is new to this integral also, you should not find it difficult understanding this. But for those who are familiar with this, it may not be very, it may all look very familiar to you. So that is one thing, but it gets, the next slides will get better and better. So we'll just see what are the, so this is my formula. So my h of n is equal to 1 by pi n sine pi n minus sine pi by 4n. So this is my FIR filter, and then what I can write here, this is why I am getting this is because of the Euler formula, e to the power of j theta minus e to the power of minus j theta by 2j, that is equal to sine theta. Good. All right, so then the next is our high pass filter HPF is given by this. H of n is equal to 1 by pi n sine pi n minus sine pi by 4n. So now what I'm going to do is I'm going to take this h of n, and then I have to, this is not, we are not stopped, we have to still find our window design. So we have not used the window design. So we are going to use one of the window design. We are going to use a Hamming window or an Hanning window for this. So your general LPF is given with this. H of n is equal to sine pi by 2. Right, so that was the low pass filter. So your h of n is given by sine cutoff of n divided by pi n, and your high pass filter is given by general HPF, that is equal to 1 by pi n into sine upper cutoff, in this case that is pi, minus lower cutoff, sine of lower cutoff. So this is a generalized expression, so which means you don't have to do this integral every time you get a question, because if you know this formula, you can guess the answer even before you show the steps for these answers. Because in my question on low pass filter, I had the range from 0 to pi by 2. So my response was 1 by pi n sine pi by 2n, right? And for my high pass filter, the range was from pi by 4 to pi, because that is always going to be the case, because the high pass filter always takes till the end. So from pi by 4, it is always going to end at pi, because otherwise it becomes a band pass filter. So when it is not ending in pi, it is ending at a place before pi, then it is a band pass filter. But the generalized formula helps you to, it helps you to save time on doing that complex, steps of all those integral and applying the limits. Now, what we are going to do is I've used the Scilab. So this is the function I'm using in Scilab. This is the code I've written in Scilab to get me these h of n values, and I got these h of n values except for the first value, which is my h of 0, and that is coming out to be NaN. So NaN means it's not a number, right? So your NaN means it's not a number, and that happens only when you get 0 upon 0. Good. So when you get 0 divided by 0, you get this not a number. So for that value, for h of 0, just like we did in low pass filter, I'm going to apply the limits. Which formula I'm going to use from limit theta tends to 0 or n tends to 0 sine pi theta by pi theta equal to 1. So when I apply that formula, I'm going to get it as 1 minus 1 by 4, that is going to be 0.75 or 3 by 4. And all the other values I'm taking from this table, which is computed from your Scilab. So Scilab is an open source, you all know that. You can easily download it and have at it. So it's very useful for at least these calculations, which could take a lot of time when you do individually on your scientific calculator. So the next step is your Hanning window. So we are computing the Hanning window. The formula is 0.5 plus 0.5 cos 2 pi n by n minus 1, and that is the code I have here. That is my Scilab program that's going to compute the window coefficients for me, and the coefficients are written here. And the next step is applying this window coefficients to my FIR, which is I'm going to multiply h of n with wh of n. So wh of n is my Hanning window. So the code on the right hand side is taking h of n and it's multiplying it with wh of n. So I'm just putting the first value, that is the h of 1 equal to 0.75, but in actual that is h of 0. That is calculated, that is obtained from the limit, applying the limit formula. So that is your window FAR. Okay. So this is, we got it. And now these are plus or minus 1 to plus or minus 5. Because of symmetry, my HW of 1 is equal to HW of minus 1. It is the same for WH also. WH of 1 equal to WH of minus 1, etc. etc. So, and we get our FAR. So our FAR is done now. Nice. And the next step is to plot the magnitude response. So we need to plot the magnitude response, right? So we have done the H of n calculation. So now let us write. So in order to find the magnitude response, first I need to write my H of z. So that is my my H of n into z to the power of minus n, right? So that, what is the formula I have? What is the generalized formula for my H of z in case of an FAR? It is given as H0 plus sigma n equal to 1 to 5 plus H of n z to the power of minus n. So my n is from 1 to 5, right? It is plus or minus 1 to plus or minus 5. Because of the symmetry, I can write it as in this manner. So I'm putting in the values of the coefficients, right? These coefficients are the final coefficients obtained after multiplying with Hanning window. So the final coefficient that is obtained after multiplying with Hanning window is used here, and that gives you a H of z to be this. All right. And now what happens is, what happens? Tell me. So this is what, causal or non-causal? Yes. So this is again a non-causal representation. So which means you are taking this. You have, we need what? We need a non-causal representation. So I need to, and not realizable. So this is to make it causal and realizable. So what I'm going to do, I should not have any positive powers, right? So this is something we do all the time. So I'm going to multiply it with z to the power of minus m minus 1 by 2, and that takes care of my positive powers. So what will happen is I get the restructured h of z. So now the coefficients are going to be restructured or rearranged, right? Because now before 0.75 was h of 0, and after my multiplication with z to the power of minus 5, it is now h of 5. So there is a restructuring of coefficients shown here, but that also take care of your non-causality. So your non-causality, which is, before it was from minus 5 to plus 5, your filter is now ranging from 0 to 10. So it is shifted 5 places to the positive axis. Clear? Before it was from minus 5 to plus 5. Now multiplying with this z to the power of minus 5 is shifting your signal from 0 to 10. It is shifting 5 places to the right side, and that makes your signal valid from 0 to 10. And now this is a causal filter because I have all negative powers, which means they're all on the right side of my z plane. And if it is on the right side, then we have a stable and a causal system. And now I can write the coefficients. H of 5 is 0.75, H of 4 is minus 0.204, H of 6 is this, H of 3 is minus 0.104, H of 7 is the same, H of 2 and 8 is minus 0.026. Okay, so these are the final coefficients. So now I have my final causal FAR coefficients, which is needed, which is much needed. And if your question is only to design your FAR window using Hanning function, you can stop at that step. So after finding the realizable causal coefficients, you can stop your computations there. That is the end of that problem. But here in this question, we also have the magnitude response. So we have to plot your magnitude response, and the magnitude response formula is given by h of omega equal to h of m minus 1 by 2 plus sigma n equal to 1 to m minus 3 by 2 h of n 2 cos omega into m minus 1 by 2 minus n. So this is the formula that we have derived in your FAR's first lecture, and that is, I am going to put my m is equal to 11 here, and then I get my h of m minus 1 by 2 to be h of 5, and so on. So I'm just expanding that for my sigma equal to n1 to 4, then what do I get? I get it in this form. So now I know these coefficients, right? I can take my h of phi, h of 1 and h of 2 from the final expression that we have on the previous slide. That is your causal FAR filters, right? Causal and stable FAR filter coefficients is what we have to use here, and then we can get to our magnitude response. So now for the magnitude response, I'm going to plug in the values from the previous FAR realizable and causal filter, and then this is what I get. And in the next slide I'm going to show you how to plot this, how to do the magnitude response plotting in Scilab. You can do it in Scilab, it's quick and easy, but if you're using an exam, pen and paper based exam, then you need to compute these values using your scientific calculator. So I'm just showing you the formulas that I've typed in the Scilab program, and you have to make sure that your omega or the frequency is in degree. So you have to multiply it by, it's in radians, sorry, from degree to radian. So pi by 180. You have to do that, and then you compute h, and then after that you take the dB calculation to be 20 log 10, and after that you plot your response. Thank you.